Hey everyone, welcome to this review. This is a review for circuits class. This is the review for EE302, specifically in which we're gonna go over one of the old exams, is 2020. In that exam, we're gonna cover several topics such as nodal, mesh, analysis, superposition, Thevenin equivalence. I think that is the main concept, okay? So sadly, I wasn't able to make it to class today, and so I'm recording this video for people. I had an interview and I just finished my interview. So this is how it's gonna work. I have my iPad here, such that I'm on Zoom here, and I'm gonna share my screen. I'm gonna go through on OneNote, start solving the questions, and going through one by one throughout exam 2 is 20. Okay, we did half of 21 in class, and we did 22 as well. So if you have any questions on any of the 3 exams, just email me right away. You have or send me a message on Canvas, whatever way is more convenient to you. Make sure you get your questions answered, because this is, I think, one of the straightforward exams. Okay, so I'm going to share my screen on my iPad here or my tablet. Let me share screen. Start now. So from here you can see my screen. And so this is how we're gonna go through this. So I'm gonna be writing the questions and then answering them through. So the first question that we have here is a circuit that looks like this. Plus, minus, this is 20 volt. This is 5 ohms, right? And this is 6 ohms. And this goes here. And this goes here, plus minus. And another 12. So this 12 ohm. This is 6 V delta. The V delta is the voltage across this resistor, and this resistor is just 1 ohm. Okay, so this is ohm as well. So the question is asking to do node voltage, and that's what I call nodal. So the way I would do is I will put a node here, call it VA, node here, and call it VB, or something along the lines. You can do whatever you want, right? You can also do VC here. The first thing you notice here is what? VA is 20 volt. Why? Because VA is the voltage from this node here, right? All the way to ground. Where is ground? It's here. Okay? So this is my ground. So this VA is the voltage from here all the way to here. If you notice, this is also the same voltage as the 20 volt. And so that's the first thing we noticed. That's the tricky part. Let's do now nodal for VB, VC. So VB, you first have to declare your currents, here, and so on. Actually, this is gonna be a little bit a hard one, because you don't know the current going through here. So we need to see how can we get over this part, right? Because this current is simple. It's just VB minus VA divided by the 6. This current here is VB divided by VB minus 0, which is the voltage at the ground, divided by 1, right? Now, but the thing is a little bit different, because now we don't know the current going through here. The reason we were able to do VB minus VA divided by 6 is that this was a resistor, and we can take care of, or use ohms law to do so. So what do we do instead? Let's do a super node, right? Okay, what does that mean? It means this, remember, is our V delta, right? So VB is V delta, right? That's something else. V delta is equal to VB, or vice versa, right? So what we do is we say, let's try to do just the normal stuff here at the super node here. So what do? We say VB minus VA, right, divided by the 6 ohms, like what just we said, and plus VB minus 0, there's the 2 here, minus 0 divided by 1, correct? plus. That's the one that we're not sure about how would we get this current here, right? And that's the what we get through. And so what we can do here is that we can take this in here, this part, this dependent source, and change it such that it is, let's say V out divided by 12. What is V out? It's VC. This voltage. It's given in the question. Sorry, I didn't write it down. So V out is VC. Why can we do that? Why can we say it's VC divided by 12? Simply because this current that you want to see here has only one direction to go, right? It's this direction here, right? And so the current that goes through this dependent source is going to be the same current that goes through the resistor, right? And so the current that goes through resistor is what? VC minus 0 divided by 12. And so this is our KCL or nodal equal to 0, of course, right? So does that make sense? This is the first current here. This is the current going down. This is the current going to the right. So the tricky part about this question is figuring out that this current here is equal to this current here. Okay, so from here we have VB, VB, VA. We know VA. We don't know the other stuff, right? So what can we do from here? What can we say about VC? Well, not directly about VC, but you can see this one here. 6 delta is the difference of voltage between VB and VC. So VB minus, this is something else that we had to notice, right? The second thing to notice is that VB minus VC is equal to 6V delta. Right? Because the voltage across here to this part here is the difference of the voltage, which is 6V delta. So as you can see here, those are the two things to notice. I'm going to put them in square to make it easier to see. So on the equation that we have up here, we can say, we can change it a little bit, such that this goes from here. It's VB now minus VA, which is 20 divided by 6 plus VB, we don't know, divided by 1. I'm just simplifying here. VC, which is what? VC is C. From here, we can derive something in terms of VC, such that VC is VB minus 6V delta. And what is V delta? V delta is VB, right? So we can say, again, more simplification. VC is VB minus 6VB, which is negative 5VB. So we plug this back in. Now negative 5VB divided by 12 is equal to 0. And then you have one equation, one unknown. You can easily solve for VB. Once you find VB, VB is the same thing as the V delta, but we just called it differently here. So you get VB, you have VA, you can solve for VC if you want from this equation back here, and then that's your V out. You see? So that's the first question. Moving on to the second question. Second one is asking to do mesh analysis. So you have a resistor here, you have a resistor here. Mesh and nodal are very iterative, right? They're the same process, but you just have to be a little bit careful every time you're doing it, and you'll be fine if you're careful enough. And you kind of notice where the current goes, where the voltage is, the stuff that we notice in class. That helps a lot, right? So this is, sorry for my drawing, but this is what the circuit looks like. Okay, ohms. You have 1.7K ohms here. You have 2K here, ohms. And then you have 5 milliamps here. And this is 150 I delta. I delta is, this is what, 5.4K ohms. This is I delta. Let's make it capital. So the first thing you want to do is what? Define your currents, I1, I2, right? Do your meshes. First mesh, what is it going to be? 2K I1 plus 1.7 K I1 plus 5.4 K times I1 minus I2. Why? Because this has the two currents going through. Oh, wait. I didn't even need to do this. I could have looked and said if I1 is what? 5 milliamps. That's why I put the notice stuff first. Now, instead of just jumping into it, I think we just do the notice stuff. What do we notice? We notice that I1 is 5 milliamps, right? We notice as well that I1 minus I2 is I delta, right? So yeah, let's do mesh on the other side only. That's all we need. 1.7K I2 plus 2K I2 minus 150 I delta plus 5.4K I2 minus I1. Don't put I delta, just put everything in terms of I1, I2, and your life is going to be easier, right? So I see I2 here, I see I2, I see I2 minus I1. So but I1 is simple, right? I1 is just a constant. I delta is I1 minus I2. So as you can see here, everything is in terms of I1 and I2. I1 is a known number. The I delta can be simplified to the I1 minus I2. So you end up with something like this. I'm gonna simplify it. I'm not gonna answer it, but it's just algebra. You can put it on a calculator. 150 times what is I delta? I1 minus I2. You remember this? You have to put a parentheses because you're multiplying this negative 150 with both. So don't make these small mistakes, right? Make sure you pay attention to them. And then I2 minus I1 equal to 0. So you see I1 and I2 in this equation, and we know I1. How do we know I1? This is I1, the current going here. So simple enough. We just plug in, and that's it, right? Let's move to the third question. It's asking for the Norton equivalent, right? So you do something like this. You have your resistor, you have your current source, you have your voltage source here, you have another resistor here, another resistor here, and then the current source here. And then you have your A and your B, right? And you have 40K here, ohms. You have your 2 milliamps. You have your 18 volt and a 6K ohm resistor here, a 2K ohm resistor here, and you have a 1 milliamp current source here. So it's asking you to do it with respect to AB. So as you can see here, AB, remember? So again, it's asking you to find Norton equivalent, right? So Norton equivalent looks something like this. Voltage source, resistor. This is R Thevenin. This is V Thevenin. So how do we do V Thevenin? If you remember, we got this here, right? And then we figure out the VOC. V Thevenin is the VOC or V out, whatever you want to call it. So in this case, yeah, and what else is given to us? Is there anything else? No, okay. Okay, so how would you do this, right? There's a couple of ways, right? You can, there's a couple of different ways you can do, to be honest. You can, you can change this with source transformation, or you can do nodal, mesh, whatever. I think nodal here is easy because you have a current, one here, and you can put the two nodes and you figure your answer out. Simple enough. Once you find the current, you'll be able to get the voltage. Because the voltage here is the same thing as the voltage here, which is also the same thing as VB. So you can do nodal and then figure out VB, and VB is VOC, which is V Thevenin. So nodal in this case is going to be VA minus 0 divided by 4K minus 2 milliamps. Oh wait, VA, we know VA. Again, what is VA? It's 18 volts. Well, let's do nodal for VB. What is VB? VB minus VA divided by 6K plus VB minus 0 divided by 2K minus 1 milliamp is equal to 0. Simple enough. We put VA, we plug it back, we get VB. VB comes to be, what is it? I don't remember. Wait, this is what, Thevenin or Norton equivalent? The question is asking for Norton equivalent, which is simple, right? It's just the same thing, but with a current source. We can do any of them, and we get the other one. We can do Thevenin and figure out Norton. Since I started with this, I'll just continue with this. It's just a source transformation, as you know, changing between them. But what is it? It is 4 times 1.5. 4 times is 6 volt. So that's your V. And then coming back, if you remember to find the R Thevenin, again, what do we do, right? We cut, sure. And then since we only have independent sources, so we take off, we shut them down. So what is a current source? It's an open. What is a voltage? It's a short. What is a current here? It's an open. And then you're looking from here, so we're gonna head this way. So you have 4K in series with 6. That's 10. 10 in parallel with 2. Which is what? 10 times 2 divided by 12. So you get 20 over 12. That's our Thevenin, which is what? 10 over 6, which is 5 over 3. What is 5 over 3? 1.5, right? 1.6, 1.5. Let me check calculator. Sorry, my brain is not working very well right now. 1.6, yeah, which is right, the right answer. Yeah. So this is how you find your R Thevenin. This is how you find your V Thevenin. And then we do a source transformation. Remember, this value stays the same. And for you to find the I Thevenin is simply equal to the V Thevenin divided by the R Thevenin. And that's how we do source transformation. Well, that's the third question. It's also asking you to do it with respect to CD. What is CD? Oh, here? It's also asking you to do it with respect to this. But it's the same process, right? All you have to do is you just have to repeat the same process, but just make sure I think the voltage. Okay, let's see. Yeah, well, first thing, I mean, not the same process, but okay, let's actually do CD. Let's put it up here because this is simple, right? CD. What is the voltage across here? The V Thevenin. It's 18, right? We already know. We already said VA is 18. So it's 18 volt. As simple as that, right? Easy. Okay. How do we get our R Thevenin? Again, we're looking from here, so we're adding the other direction. So you have what, 2 in series with 6, right? Right. 2 here in series with 6, that's 8. 8 in parallel with the 4. Is that right? Or did I miss something? Wait, give me 1 sec. Let me look at the question again. This is open, 2, 6, 8. 8 in parallel with, this is 40K. Oh, sorry. 40. Okay. Wait, so R Thevenin here is what? It's not 10 anymore. It's 40K. 40K plus 6. That's 46K. 46 in parallel with the 2. So 46 times 2. That is 48. 46 times 2 which is what? 92 divided by 48. What is 92 divided by 48? 92 divided by 48. Isn't 92? Wait. 46 times 2. 92 divided by the sum, which is 48. And what am I getting? 48 equal to 1.91. Okay, let me see something. Let me double check something. Okay, so let me tell you what happened here. I noticed I made a mistake, and that's why I like to draw this more than once, instead of doing this lines and stuff that I did here. But this is a short here. This is shorted, so you have a short between these two, right? And then now, but this is in parallel with nothing. So 40 in parallel with nothing is gonna be 40 times 0, because this is 0 resistance. So now this is 0. And then what you have on the right hand side is 6 in series with 2. So that's how you do it here, not this. So you do 6 in parallel with 2. Again, think about this. This is 40 and this is a short, right? So 40 in parallel with a short is what? It's 40k times 0 divided by 40 plus 0. So it's a 0. That's why it's a 0. But since we're still looking here, we move on and we look into this other side here. This is out now. This is completely out since we're looking at AB, okay? This is looking at AB. And then you have 6 and 2. So what you do is you do 6 times 2 divided by 6 plus 2. So you end up with 12 over 8. And that's 1.5. This is correct. On the other side, because now we're looking at CD, remember? We gonna be looking at this part here because now this is 0, right? And so, well, we're looking from this side, right? So the way I taught you is you go from here, right? So 2 in series with 6 is what? 8, right? 8 in parallel with 0 is 0. 0 in parallel with 40 is 0. So the R Thevenin here is 0 ohms. So this is a little bit weird, but short means there is no resistance, right? Short means R is 0. Open means R is infinity. Right? Because there is very, very high resistance that there's no current at all. There's no thing at all. That's what it means. So that's the two different ways. Let me know if this makes sense. Yeah, I made a mistake while drawing. I didn't notice how it looked like. I didn't notice that short because I tried to draw over what I had. But you want to make sure that you notice this one. So for the last one, it's also asking for the R Thevenin. So it's very similar stuff. You do a current here. You have this. You have that one going in here. You have your resistor, your other resistor here as well. This looks here. This is a voltage source, and you have B here. That goes this way. R2. This is R1. Okay. It's asking you to find Thevenin resistance, R Thevenin with respect to AB. So it's asking you to find it with respect to here, A and B. This one is what is it? So this one is given as IX. This one is beta IX. And so yes. So this has dependent sources. So if you go back to the notes, the way we do dependent sources is that we insert a voltage source of 1. And because of this here. And we try, so the voltage is 1, and then we find I. And R Thevenin in this case is V equal IR. So it's the V divided by the I. I'm pretty sure something like that. Yeah. So, so this is how you do it. So you will have. I feel like a lot of people are not clear on this part, but we have to make sure that you guys understand this one. So, what is my I test? This is gonna be my I test. Okay. So this I test is between the A and B. That's what we're doing. That's the test current that we're inserting. If you notice, this I test is gonna split here, but it's gonna come back to IX. So we notice that IX is I test. Just the way it goes through, right? Okay. And so we can do a KVL in our case. So this is your V test. You can set it to whatever, but let's say it's V test at this moment. So it's negative V test, negative V test, V test, negative V test, plus what? Plus what? Anybody knows? Well, what is this one here? What is this current? This current is beta times I test, right? Because IX is I test. That's what we got here. Okay. So the current is say going through I1 R1. It's gonna be what? Again, we can simply do a KCL at this point, right? We know I test is coming this way. We know this current is coming this way, so we can figure out this current here. Whatever is going in is equal to whatever is going out. So what is going in? Whatever is going in is what I test is going in plus beta I test is also going into the node, and what's coming out? Let's say it's IR1. So IR1 is equal to, if we took I test as a common factor, I test is going to be 1 plus beta. So this is IR1. That's the current going through R1. So if you want to find the voltage across R1, we just multiply this by R1. So I test here times 1 plus beta times, this is the current. We need the voltage, so we need to multiply by the resistance plus this voltage here, which is what? VO plus VO is equal to 0. Now we made our entire circle back, right? We went through here. So we went through here, B to A. We came through, we figured out the voltage across here. And then now we have the voltage across here. So back at the start point. And that's our KVL, right? This is our KVL that we made. So we ended up with something that looks like this. So we know the I. No, we did, sorry, this is your KVL, right? And yeah, and from here you can simply figure out how would you divide the V test divided by the I test, because our Thevenin is V test divided by I test. So solving across from here, you'll be able to figure out the I test in terms of the V test. But yeah, I think that's pretty much all the entire exam. So the tricky part is figuring out the current here for this question. The tricky part here is I made a mistake, but I would, don't do what I'm doing here. Try to actually draw the circuit on your own, away from the question itself, such that you can look at it and see all the different changes on the sources. So that was the tricky part. It just, this resistance is 0. And the tricky part here was recognizing that this current here is the same current going through the entire loop. And so it's also the same current as VC divided by this. I think that's it for the exam. If you have any questions about the exam, let me know. Again, ping me on Canvas, send me an email, do whatever you need to do such that you can get to your questions. Good luck with the exam and let me know how it goes. We're gonna meet again on Thursday, but this is gonna be uploaded on YouTube for your reference, okay? Have fun, and I will see you on Thursday after the exam.